Yes, sir.
There are some small issues. Should I teach for some time and then go to the whiteboard or red board or whatever it is? I have to cover something in the class, then only I can go to the whiteboard. Okay? Is that okay with you?
Yes, sir.
Okay. So there are a few things which I have to tell you before I start the classroom. We were trying to look at the examples, and we were trying to see what is the Young's inequality or something like that last time. And as soon as we finish the examples, let me start with the whiteboard and then tell you what is the issue with the topology. That is what is perhaps is creating a problem. So let me now share the screen to you. Okay. What has come? Just 1 minute. Just hold 1 minute. I'm sharing the screen. Can you see anything? Can you see the notes?
Yes,
Yes,
sir.
sir.
Okay. So we were trying to do the Young's inequality. AB less than or equal to 1 over p a raised to p plus 1 over p prime pp prime. 7.2. Condition is that a and b both are positive. So I said that the proof, there are many proofs. One of the proofs given here is using the fact that the logarithm is a concave function. So as a consequence, what you have on the fourth line, 1 over p log a raised to p plus 1 over p prime log a is less than or equal to logarithm of 1 over p a raised to p plus 1 over p prime b raised to p prime. This is the consequence, the last line, the inequality is a consequence of the fact that log is a concave function. I sent a notes to you on that. I hope you have received it. Now what you do is now we use this inequality to prove the Holder's inequality. Holder's inequality is a very important inequality. If p is 1, as I told you last time, we set p prime equal to infinity. And if p is infinity, we set p prime equal to 1. Condition is that 1 over p plus 1 over p prime equal to 1. That is, p and p are conjugate exponents. So idea is to introduce a norm onto this LP spaces. So first, to show that something is a norm, we have to prove the triangular inequality. That is where this Holder's inequality is used. So the 7.2 proposition. Take any xy in Kn. Kn means Rn or Cn. You can work with Cn, Rn first, and then we can do it. So x has coordinates x1, x2, xn. Y has coordinate y1, y2, yn. So you can look at mod of xi into yi, okay, and sum it up, I equal to 1 to n. Then it says it is the p norm of L x into p prime norm of y. That is what is called the Holder's inequality. I'm only stating a Holder's inequality. I'm not giving a proof. I'll prove it in a moment. Okay. If x is 0 or y is 0, this inequality in 7.2 is trivial. Okay. When p is 1 or p is infinity, then also this is simple. Nothing great about that. That's the triangular inequality what you use on the real line. That is what is used. So let us take x not 0, y not 0. And let us take one line between, p lying between 1 and infinity strictly. Okay. Now if that is so, what we do is, what we want is summation I equal to 1 to n xi yi. So where do I get an inequality in terms of, I have xi yi, but I need to get something in terms of, if you see this inequality, Young's inequality, right? You have a, b, right? A and b, and look at the right side. It is written as sum of something in terms of a raised to p, something in terms of b raised to p prime. That means, to certain extent on the right side, you don't have a and b together. Either the term is with a or the term is with b. That's the idea here. And you look at the Holder's inequality, it also says similar thing. What does it say? It says that the left side is a product of xy and yi, whereas the right side is norm x into norm y. So this norm x raised to x, p norm is independent of y. Norm of y is independent of x. But the left side, you have xi, yi coming together. That doesn't happen on the right side. So the idea is that try to separate out x and y, and that's where we use the what is called. So what you do is you take the summation mod xi yi, write it as summation I equal to 1 to n mod xi yi. Okay. And if you want, you can divide by norm x raised to p on both sides. Everything is positive. So now what you do is this mod, this will be, so you have two elements here. This a will be norm xi over the denominator. B will be mod yi divided by denominator. So apply the Young's inequality. So that will be, sorry, you take a as mod xi over norm x power p, rather norm of x, p norm of x, and b to be yi divided by the p prime norm of y. Apply the Holder's, the Young's inequality. You get 1 over p times xi raised to p over norm of this p plus 1 over p prime. Now you see the summation in this term here, that xi and yi don't get multiplied. They are separated. That is the idea. Why should we need this idea? You would need this idea because if you want to reconstruct the proof, you can do it without putting strain on the memory. So idea is to separate out here. Okay. So now you split this sum into two sums. That can be done. Summation of ai plus bi is summation of ai plus summation of bi. So this first summation will be 1 over p. This xp norm is independent of I, so it comes out. So 1 over p into 1 over the xp norm of p raised to p, because there is a p on the top here. Okay. And you have summation I equal to 1 to n xi raised to p plus 1 over p prime, this yp prime. Okay. That is the next step. That's the simple calculation. Now what you have to simply see here is that this summation I equal to 1 to n mod xi raised to p is nothing but the p norm of x. So this will be the p norm of x divided by the p norm of x cancels, you get 1. Can you cancel it? Yes, you can cancel it. The reason is x is not 0 and y is not 0. Same story with the second term. So what you have, this is cancellation of x raised to p and y raised to p in the two terms, leaves with 1 over p plus 1 over p prime. But we know that p and p are conjugate primes, conjugate exponents, sorry. So therefore, this 1 over p plus 1 over p prime is 1 because the first term Rm x raised to p cancels with the Rm x raised to p in the denominator. Same story with the second term. Look at the first term and the last term. 1 over Rm x raised to p, y raised to p prime, summation xi yi is equal to 1, first and the last term. So that is what the Holder's inequality. You push this Rm x raised to p, Rm y raised to p on the right side. What you get is I equal to 1 to 1 mod xi into mod yi is actually less than or equal to mod x raised to p mod y raised to p prime. That is what okay. 1 minute. Okay, and this PC is running on power low. I'm switching on the connecting it to the power. Sorry. So that is the story. As a consequence, what we have is if 1 is lying between 1 and infinity, then this whatever the norm p that we have defined is actually a norm on Kn. And not only that, if 1 is less than or equal to p less than or equal to q, then this norm of x q less than or equal to norm xp, this also I explained to you last time. I'll come back to this later. Okay. So in order to show that it's a norm, what is that we have to show? We have to show three things. One is the homogeneity, second is norm p x equal to 0 if and only x is 0, and the triangle inequality. Okay. So let us take a to be any element of the scalar k and multiply a by x into p. So what is this scalar multiplication? It is pointwise multiplication. So this is by definition I equal to 1 to n mod of a xi raised to p raised to 1 by p. This is same thing as mod of this whatever this alpha raised to p into mod of xi raised to p. So what you do is you remove this mod alpha out here and you write it as alpha x raised to p. Okay. So it is as simple as that. Do you understand the last step? This mod alpha raised to p is a constant. It comes out of the, it's independent of I, so it comes out of the summation sign. So mod alpha raised to p raised to 1 over p will be mod alpha. And what remains? Summation I equal to 1 to n mod xi raised to p. That is the whatever the mod of there's a typo error here, okay? Mod alpha into x raised to p. That is the, it's a small typo error here, don't worry. Now the second thing that we have to show is the triangle's inequality. Now you look at mod of x plus y raised to p, okay, norm of x plus y raised to p smaller than or equal to norm of x with respect to p, norm of y raised to p. That is what we have to show. So what we do is we calculate x plus y norm p, but calculation is difficult, so we raise it to p. Why do we raise it to p? Because that exponent 1 over p will go up. So x plus y raised to, the p norm of this raised to p will be summation I equal to 1 to n xi plus yi raised to p. So that power 1 over p and into P will be just 1. Okay. All right. Now what you do is you write this xi plus yi as xi plus yi into xi plus yi. So there is a power p here. So we have taken one power here. So it becomes p minus 1. Why are we doing this circus? This circus we are doing because we want to use the Holder's inequality. So Holder's inequality, it says summation ai bi is less than or equal to the LP norm of A into L, LP prime norm of B. That is what we are doing here. So you take this one here. Just one comment here. If xi and yi are either complex numbers or real numbers, summation of this xi plus yi raised to p is finite because the summation is finite. This n is fixed. Okay. Similarly, this xi plus yi raised to p minus 1, if you call it as zi, that is also finite, and if you sum it to the n, it's also finite. Raised to q also is finite. Therefore, no issues with that this belongs to LP or L2 is not a big issue. The reason is that the summation is finite. We are still working on the vector space structure. That's the reason why we don't need a topology. So this thing will be what? You split this into, okay, this whatever that we have here. Mod of xi plus yi is smaller than or equal to mod xi plus mod yi. Write that here. And now you split this sum into two parts. Less than or equal to is important because you have split this mod x plus xi plus yi as less than or equal to mod xi plus mod yi. So this term will be multiplied by mod xi, that's one term. Second term will be mod yi into the second term. So you have the Holder's inequality, the stage is set for applying Holder's inequality. This xi, mod xi is ai, mod xi plus yi is bi. So you have summation ai bi, apply the Holder's inequality. So you get the next step. It's a question of writing out the text. The same story here, okay? So this mod ai raised to p is this, and the other one is, if bi is what you have, then it is the norm of bi in the LP prime norm. What is that? You take summation xi plus yi, right, raised to p prime. That is p minus, there is a p minus 1 here, multiplied by p prime, raised to 1 over p prime. That's what you have. The same story here, instead of, exactly the same. Now, if you see here, what is common here is this part. Summation I equal to 1 to n xi raised to p minus 1 into p prime into 1 over p prime. That's the common factor. Okay, take it out. What you have here, norm of x raised to p, norm of y raised to p. That's what you have. A bit of rearranging the term. The moment you do the rearrangement of the term, now we have to simplify something. This 1 over p plus 1 over p prime is 1 is equivalent to saying p prime is 1 minus 1 over p raised to minus 1. That's as good as saying p over p minus 1. So what you do is you take this value of p prime and push it into the inequality that we have done. That will give you that mod of xy raised to p will be less than or equal to whatever this xy plus p raised to p prime. X plus y is not 0, and then you have the triangular inequality is what is used. So this gives you the what is called the inequality is obvious if x plus y is 0. So norm of xp is right. I hope it is clear to you. Okay. This last step norm of x plus y raised to p. You see, what you want to show is norm of x plus y raised to p less than or equal to something. But I have a power p here. So raise it to 1 over p. To raise it to 1 over p, what you have here is that you will get is p minus 1 over p. Okay, that will be, that's exactly what we are using here. Instead of p prime, okay, you use that part. So it's a simple calculation here. If you use p prime equal to p over p minus 1, this is what you have. Okay, so you raise this to 1 over p, you will get an norm of x plus y. As simple as that. I don't know whether you are understanding what I am saying. The last step I will repeat. X plus y norm p raised to p is less than or equal to norm x raised to p, norm y raised to p, multiplied by norm of x plus y, p norm of p minus 1. You shift this on the left side. You have a p here, you have a p minus 1 here. So p minus 1 will be plus 1. So when you shift this norm of x plus y raised to p minus 1 on the left side, what you get is there's a power p already here. So x plus y raised to p minus 1, that is p will cancel and then you get a 1. So norm of x plus y raised to p will be. So I'm just saying you shift this x plus y raised to norm p raised to p minus 1 on the left side. When you divide, you have to make sure it is not 0. This is the place where you use the fact that x plus y is not 0. Okay, that's what I am trying to imply upon. Since x plus y is not 0, you push it on the other side. All right, so that's the story. Oh, by the way, if x plus y is not 0, then we get the triangular inequality. If the x plus y is 0, then it's an obvious affair. If x plus y is 0, then you can take x equal to minus y and you can rewrite the inequality, then it becomes obvious. So whether x plus y, why all this circus is done? Because I have to shift this x plus y raised to p minus 1 on the left side. So I have to divide out by that factor, for which I need x plus y not to be 0. Okay, assume x plus y is not 0, you get the Holder's inequality. Now prove the Holder's inequality, x plus y is 0. That's an obvious affair. That's not a big thing. Right? So that is the Holder's inequality here. Now we have assumed that this result is true for one strictly less than p less than infinity. So what happens when p is 1 or infinity is a trivial matter, and I will allow you to do it yourself. Okay. The next one is a simple calculation. I will not try. Okay. So that is the basic concept of the fact that the norm actually satisfies the triangular inequality. Now we come to the sequence process. Now we discussed this last time. I have explained to you what is the sequence process. Most of the scene, as most of you have seen, the metric space in the exposition will be rather brief. Brief means that we have already done what we want. Now SP, the set of all sequences on K. I have told you what is a sequence. It's a map on the integers to whatever the thing. Okay. We define a vector space. All right. Please note this X has infinite components. X0, X1, X2, Xn, dot, 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 dot. Okay. This we write it in a brief as the bracket Xi. Whatever bracket you want, you can use it. Now this sequence space, now we make it a vector space. How do you do that? You have to define two operations. One is the addition operation, another is scalar multiplication. So if you take two sequences x and yi, then you define this to be xi plus yi. That is point-wise additions. Okay, component-wise addition if you want. Alpha xi is alpha times xi. component wise scalar multiplication or point wise scalar multiplication. These are the two operations that we define on S. How do you define a vector space? If you have a vector space, you have to define two operations. One, an addition. Two, scalar multiplication. So on this sequence space, we have defined two operations. Then it becomes a vector space. Okay. So the story is that given this vector space, now you take 1 less than or equal to p less than infinity, we define norm of the sequence xi to be summation I equal to 1 to n mod xi raised to 1 over p, same LP norm, if p is not infinity, greater than or equal to 1. If p is infinity, you define it as the supremum of I over n mod xi. That's the maximum of all the components. These are the two norms that we define between what p lying between 1 and infinity. For 1 less than or equal to p infinity, we use the summation. For p equal to infinity, we define it as the supremum norm. Okay. Usually, when p equal to infinity, since we have written supremum here, it is also called a supremum norm. Okay. These p norms need not be finite for all sequences. Why should it be finite? Okay. For example, you take a sequence, say 1, 1, 1, all elements are 1. Now, when you add 1 infinite times, and if p is not infinity, then the summation, when p is not infinity, 7.4 is infinity. So, there is no reason why this p norm should be finite. And therefore, now, so the question comes, why is it happening? It's happening because we have infinite summation. If you are on the finite summation, there is no problem. But if you are on infinite summation, then it creates a problem. Okay. So what we do is we don't worry about the case when summation is infinite. Okay. So we write small LP, L with a subscript P, normally written as LPK. K denotes the scalars or complex, the scalars, either complex numbers or the real numbers. This is all the sequences, whatever that big set, such that the LP norm is finite. Okay. All right. So this is true for 1 less than or equal to p, etc. Now, second sequence space we define is C0. C0 equal to k, for which the sequence xi belonging to x and the limit is 0. That is, consider all sequences which has limit 0. Okay. This is called C0. So what we now show is that the small LP and the C0, they are actually nonlinear spaces. Okay. So what do we do first? For this, we prove the Holder's inequality. For 1 less than or equal to p less than infinity and x in LP, y in LP prime, then summation xi yi is less than or equal to norm of x raised norm of xp into norm of y. This p and p prime are dual conjugates. Okay, exponent conjugate. That is 1 over p plus 1 over p prime is 1. This proposition is simple. Why? It is simple because whatever the Holder's inequality we have proved there with I equal to 1 to n, you take that and then you get a summation here in Ln, but you increase it to infinite number of terms. So this is right side becomes a bigger thing. Now, since the right side is independent of n, you will let n go to infinity on the left side, you get that. Okay. Is this clear or not? Huh? 7.4. Should I write it and show it?
Yes, sir.
print it and show it. Okay. Is the screen visible?
Yes, sir.
What we have shown earlier is that summation ai bi, here it is n, less than or equal to summation up to n mod ai, here you have raised to p raised to 1 by p into summation is n mod bi raised to p prime raised to 1 by p. Okay. Now you take this sequence ai in LP. What does it mean? It means summation mod ai up to infinity is finite. Okay. So this term what we have here is less than or equal to norm of the sequence ai sequence ai with respect to this norm p is finite. Same way, this one will be the sequence bi with respect to p prime. Okay, this now. So this will be less than or equal to that. So what we have here is the summation n. You can take ai be a positive. Okay. Okay. That will be less than or equal to the pth norm of ai, sequence ai. Okay, it's something. This should be plus, no? Okay, it's a plus. Plus the pth norm of bi. This thing is independent of n. Why? Because summation is up to infinity. On this side you have n here. Now you take the limit. When you take the limit n going to infinity, what you have is summation mod ai into mod bi. This is n. That will be less than or equal to this one. That means the summation ai that means the summation ai summation mod bi is less than or equal to this is a sequence ai in the LP norm plus the sequence into the sequence ai. Okay, if you want you can add a plus here. So this is what we had. This is what he said. So let me see what the notes he said. Just 1 minute. I'm hoping the other PPT. This is do the screen share. Can you see it?
Yes, sir.
What I was saying is this mod of SI raised to, instead of I equal to 1 to infinity, you take it from I equal to 1 to n and apply the holders here, okay? And then you see that the right side is independent of n, so take the left side also as this one. So that gives you the partial sum. So this is what is called the holders inequality. This is still not the triangular inequality, okay? It's still a holders inequality. All right. So that's standard holders inequality in the infinite spaces. Same thing is true for LP spaces also. Okay. Now what we show here, the next theorem, is that 1 less than or equal to p less than infinity. This LP with this is a norm. C naught with this is a norm. Not only they are non-linear spaces, they are also Banach spaces. What is the meaning of saying they are Banach spaces? It means that the uh, the topology that you have, it gives you complete, it becomes a complete metric space. What is the meaning of complete metric space? Every Cauchy sequence in LP or C naught converges in LP or C naught respectively. Secondly, you have this inclusion. L1 is contained in L2, is contained in A3, etc., etc., which is normally written as LP is not less, is not contained, is contained in LQ but not equal to LQ, provided P is less than or equal to Q. Okay, and that is not contained in C naught. That's also an obvious effect. So what it also says is that finally, exactly what it means is that if you take any x in LP, then it is also in LQ. So the norm of x, the qth norm of x is smaller than or equal to the pth norm of x, LP norm of x. This is true if one is less than or equal to p, less than q, less than q. So that is one issue that we have to say it. Okay. Not a very difficult stuff here. Somewhere on the way, I don't know why Minkowski's inequality has not come. I just say it. This is folder. Yeah. This is what I was telling you. This theorem 7.2, that this norm of this P is a LP norm on Kn. That's what we had shown. That's what we are using there. Okay. I hope you are with me. Let me explain to you. What it says is that if you take finite n, this norm 7.3, this norm p is a norm on kn. It's on kn. Okay. What is the meaning of saying this norm p is kn? That mod of x raised to, okay, I'll just explain to you in a minute. Okay. Just 1 minute. See, the headache with this online teaching is that every time when you have to share the screen, I have to keep changing the whatever the presentation. Okay. All right. What we had shown as a norm is that norm of AI. Let me take A equal to n components. Okay. And B equal to B1, B2, BA. What we had shown was this A plus B in the pth norm is less than or equal to the norm of A in the P plus norm of B in the P. What is this norm of A in P? It is nothing but summation mod AI raised to P raised to 1 by P. That's the norm. Okay. What we had fixed here is this, the number of elements, number of components here was n. Okay. Now what I am saying is that if you take AI as a sequence and a sequence BI, okay. Now you look at finite sum, okay. So what we have, this one, okay. You look at the finite sum here, okay, up to n, A plus B, B, that will be less than or equal to summation I equal to 1 to n mod AI raised to P raised to 1 by P plus similar term. Now what you do is you keep it less than or equal to same thing and you raise this summation to infinity. This one plus something. Why you can do this? You can do this because you assume this AI is in LP. What is this LP? LP is set of all sequences for which summation AI mod raised to P is finite. So this is finite. Alright? The moment you make this infinity, this is independent of n. Now what you do is you let this n go to infinity here. Letting n go into infinity. What you get is this norm of A plus B in the LP norm is less than or equal to norm A plus norm B. So what you actually prove is in the finite dimension and go through the what is called this the Holder's inequality and go through the limiting process, you get the required thing. Okay? 9:56. I'll stop here because some of you may have a class. I will not bother you to. So next time when we meet tomorrow, if you have any doubts on these matters, this is very, very fundamental. Please understand this slowly. I don't mind spending 1 or 2 hours more on this. I can take the PPT again, explain to you on the with the whatever that tablet I have. I will write it and show you. Okay. Have a good day. Enjoy your day. Bye.
Okay, sir. Thank you, sir.
Thank you,
Have a
sir.
nice day.